Okay, so your lab number 5, slightly delayed, but you will still get 2 weeks to do it. For lab number 5, I'll definitely make sure it's released by the Tuesday class next week. But I'm going to adjust the deadline to be still, you got 2 weeks to do it. So the last day to submit the term work will be December 3rd. I'm going to make it a due date. So it'll still be fine. You still got 2 weeks. Okay? And then afterwards, we got maybe about more than 10 days of gap before the exam. So we can also schedule some review session. I'll reach out to you about that. But lab number 5, got to be done. Okay? By Tuesday class, you will see the lab. And your written test number 2 will be next Wednesday. That's going to be the last test before the exam. And I released the guide. I released the practice question. All right, so make sure you read them through, and then especially be clear about the coverage for the test. Okay, check it out. And there will be another bonus opportunity coming. So that'll be the final formal course evaluation. So we're going to follow the same criterion. So if the collective response reach certain limits, like a threshold, and then we'll give bonus to you guys for participation. It's going to be completely anonymous, but it'll be nice to hear your feedback for the whole semester. I'll reach out to you guys about this course survey. I believe that's going to be launched on Monday. So I'll reach out to you. Okay? All right, guys. Any question you want me to clarify about the course? Anything? Yeah, your programming test number 2 is still being graded. I need to follow up with the TA, but I'm hopeful that I can release the marks and the feedback early Monday as well. Okay? That's something I can say for now. All right, if no further questions, why don't we go to the recap from Tuesday. So from Tuesday, we continue with the bridge controller, especially the first refinements. Especially, we try to also derive the guard for MLN. Just remember, in the concrete model of M1, the first refinement, we actually got 4 events. We got ML out and ML in. So these are the concrete events. And today we'll also touch upon another 2 events. So these are the events that's newly introduced in the M1 model. And we're going to see how we can argue about their correctness. We'll get to them. And by the way, whatever we cover today, it will be also the ending coverage for written test number 2, just to let you know. All right. I'll confirm the slide number after today's lecture. We'll see how far we can go. All right. But if you got any questions, just slow me down. All right, so that's about the guard for MLN. And don't forget, for ML out, we actually derive it using several equations. That's something you want to really go through and make sure you're convinced. Okay. And we talk about some comparison, right? We got abstract events versus concrete events. We got abstract guard versus concrete guards. And for invariants, we got 2 types of invariants. We got a so-called linking invariants, which will link the concrete variables A, B, and C with the abstract variable N, right? Linking between M0 and M1. Also, we got a safety invariance here, which correspond to one of the requirements for the bridge controller, which says it should be one-way. All right? And by the way, for one-way bridge, this is not the invariant that we could specify M0. There's no such like a concreteness for us to specify, since we only got N in M0. All right, and then we talk about how you can see for every concrete transition, there should be some corresponding abstract transition as well. But what we didn't speak about last time was, let me talk about very briefly. So ML out has its corresponding abstract version in the M0. MLN also has its abstract version in M0. What about IL in, IL out? Since they are newly introduced events, they don't really exist in M0. So it turns out, conceptually, we have to have some artificial events called skip. Right? We'll see if we can get here. And then once we get to skip, I'll explain to you what that really means. All right? But bottom line, every event, including the concrete events and also the new event, should have some counterpart in the abstract world. They should. All right? That's something we'll get to. Okay, and then we talk about before, after predicate. Just remember, sometimes in the action itself, even though we only talk about C, and that means C should be changed, but A and B not really mentioned, meaning that A should remain the same and B should remain the same. So when you work out the before-after predicate, you just got to say A prime equals A, B prime equals B. Right? That's straightforward. And that's the formal components. You can read it through. And we talk about 2 background pages for you to understand the guard strengthening proof obligation. The first one is about predicates being stronger versus weaker. So given 2 predicates, for example, you're given the guard for the concrete, and you're given the guard for the abstract. If you say there is a formal implication relationship between them, that means the left-hand side is stronger, and the right-hand side is weaker. And the way to visualize it is to see each one of them corresponding to some corresponding set of satisfying value. The stronger one should have smaller one, like a smaller set, because it got smaller, it got fewer satisfying values. On the other hand, the weaker predicate should have a larger set, right? So we talk about how you can visualize them as set comprehension notation, right? There will be a subset relationship between them. So stronger versus weaker. And we talk about guard strengthening. Guard strengthening simply tells you that whenever you want to create a new refinements, for every abstract event, when you create a concrete event, you want to make sure the guard in the concrete world is strengthened, meaning that it should become stronger. So this is why when you actually see the proof obligation, we got a concrete guard implies the abstract guard. So it's stronger. All right? That's a connection you want to see. And of course, you can go over 1, 2, and 3 about the background, right? I'm not going to repeat. But just notice that this is something that's not correct when you say the abstract guard implies the concrete guard. That's not right. On the other hand, there are 2 ways to say the right thing. Either you can say the concrete guard implies the abstract guard. That's good. Or you can apply contrapositive to say not G implies not H, right? Not here implies not here, right? There will be another way for you to interpret that, which I also talk about on Tuesday. Right, so I think that this page here contains much information that you really want to go through and digest before the test and before the exam. All right, and then the final thing that we spoke about on Tuesday was to look at this particular proof obligation, which is new to us. That one there tells us if you have some refinements, let's say M1, you want to make sure for every concrete event that's overriding the abstract events, we want to make sure the guard over here is stronger. That's why it's called guard strengthening. We want to strengthen the guard, we cannot weaken it. Okay? So here you can see the guard here has the index I, meaning that it's going to be indexed by the list of concrete events. In this case, since we got 2 concrete events, so we should really get 2 sequences generated, right? Whenever you got some index I, either index for invariants or index for events, you know that there should be multiple sequences that should be generated, right? So when you write the test on Wednesday, be very clear about the number of sequences that should be generated for different kinds of proof obligation. That's also very important to bear in mind. And we spoke about how you can, let's say, based on this proof obligation rule, for one of them specifically, you can see we got ML out, we got ML in, so 2 of them. For ML out, simple. You just got to make sure you can see the concrete guard is included here. Sorry, beg your pardon. Concrete guard is included here. And the abstract guard is included over here. All right, you can see the correspondence. What about the rest? The rest of the hypotheses will just correspond to axiom, abstract invariance, and concrete invariance, right? All right, so that's the proof sequence that we formulated on Tuesday, okay? And your exercise would be to try to formulate this one yourself. And once you have done that, you can compare the answer on the slides, okay? Any question about what we said on Tuesday? If no, I think the next step will be we'll try to prove them, all right? I think today we'll touch upon many proof obligations that we don't necessarily have to prove all of them, but I think some of them do can really help you if we go over together. So why don't we do that? Let's do the beginning 1 or 2, all right? Let's see the first one. So we got these 2 proof obligations. Let's say we try to prove both of them. Okay, both of them. The first one here. All right, the first one here has to do with the strengthening of guard for ML out. And this is the sequence that we are given to show provable. It may or may not be. You got to show it. All right? And as a hint, these are the relevant rules. In the actual test or the exam, I may not tell you which ones are relevant. So you will have to find out which ones are relevant. But for now, to save time, also to help you practice, it's OK. Why don't you guys stare at this sequence a little bit? Well, remember the tip. We always may want to apply monotonicity first to only keep the relevant hypotheses. That's going to help us. OK, I'm going to do the proof together with you to go over. But why don't you just think to yourself, if you were to do this, what would be your first attempt to drop the irrelevant hypotheses? While you're thinking, I just want to do a little bit of annotation for you. So these two are the axioms. And these two are the abstract invariants. And these are the concrete invariants. And these are the concrete guards of ML out. Of ML out. Finally, we got over here, this guy here would be the abstract guard of ML out. All right, OK. Of course, if you really prefer like to be isolated when you think about proof, that's OK. Just practice after the class. OK, to save time, let me tell you, one way to prove it would be we can choose 3 hypotheses only as relevant. OK, let's take a look. I can choose, for example, let me make it bigger, this one here, this one here, and this one here. Another tip for you, which I sometimes try myself, right? You don't necessarily have to think about the exact inference rule just yet. Try to kind of calculate in your mind, kind of sketching the idea, right? It would be very grateful whenever you got actually some equality in the hypothesis. They are usually useful, okay? For example, here I got C equals 0, right? That means I can somehow apply C here to be 0, which can be canceled out. And then I got A plus B equals N. Agree? And then A plus B can be used to substitute A plus B here, which can be N. And then I got N less than D, N less than D. Done, conceptually. Of course, you cannot just write out what I said in words. You got to write in proper proof sequence, right? That's really something you can usually spend maybe 1 or 2 minutes to think about what could be the plan, and then try to write it out in the proper format. All right, let's now do it. Step number 1. Let's now apply monotonicity. And then I'm going to leave only one A plus B plus C equals N. A plus B less than D. Turnstile. Oh, sorry, I got one more. There we go. And then C equals 0, turnstile, and less than D. That's what I need. All right, that's the first step. I only keep these 3 hypotheses. Everything else has been dropped. And then I'm going to use EQLR. I want to somehow make use of this. Okay, C equals 0. And think about this one here is the left. Right, I can make a note here. Let's say this is the left, and this one here is the right. Okay. Okay, I'm going to apply EQLR, meaning that I'm going to substitute every occurrence of C by 0. So we can do EQLR, and it would be allowed if you try to do EQLR together with monotonicity at the same time. Because usually, after the substitution has been done using this, you can drop it at the same time, right? Unless you plan to do like a multiple substitution, but it shouldn't be, okay? So I'm going to say EQLR and monotonicity. This is one of the very few occasions you will be allowed to write multiple rules in one single step. In the exam, for most of them, you should really write one step at a time, okay? All right, let's now try to do that. So if you want to replace, basically this one has to be replaced, and that's it. Actually, that's the only one, all right? So let's now do this. After this, I got a plus b plus 0 equals n. A plus b less than d, and c equals 0 has been dropped, and less than d. So that's the new sequence. We're getting very close. Right? You can see I'm basically following the informal strategy I kind of verbally mentioned to you. Okay? And you cannot really apply EQLR just yet, because somehow we got plus 0. So you need to apply maybe some arithmetic rule. You can say plus 0 has no effect, so we can cancel that out. So by some arithmetic over here, you should really detail that. You can say, for example, a plus b plus 0 is simply equal to a plus b. And we say that is equal to n. Okay, that'll be good enough. Okay? And then we got a plus b equals n. A plus b less than d, turnstile, and less than d. Okay? Okay, so far so good. And what should we do next? Basically, we want to somehow replace this guy over here by n. And indeed, there's an equality here. Right? Once we replace it, we got hypothesis appear in the goal as well. Done. Okay? Let's now do that. So here we can say EQ, LR, monotonicity at the same time. So again, you can say this part over here is the left. And this part over here is the right. Okay? Oh, right. That's right. EQR. So we're going to replace every occurrence of a plus b by n. And by the way, so here it's quite straightforward, a plus b equals n. But watch out, the order is really important. Hypothetically, if somehow I give to you in the test or exam, if this turns out to be n equals a plus b, it's not correct anymore to say EQLR. It should be EQRL, because I'm replacing the right-hand side by n. Okay, just to mention. So you got to watch out the order. That's why we got both rules already. And of course, there will be no hint like I will introduce this one. Let me finish this, and I'll get to you. Just one moment. Yeah. All right, let's now do replacement and monotonicity quickly, and I'll take questions. Bear with me. All right, so we're going to replace the a plus b over here by n, and then drop this one here. All right? So what we got is n less than d until n less than d. And indeed, this looks very promising. You can see that n less than d basically like a p here. And the n less than d is like a p here, right? We do have some matching rule, terminating, all right? So the final one to say would be, now we got hypothesis. So that'll be the terminating one to say it's done. All right, so that tells you done. Question? Oh, I see what you mean. Okay, sure. Yeah, that will work. So your classmate was suggesting, let's say hypothetically, if you were given, let's say, n equals a plus b, for example. If you apply arithmetic, yes, you can just say commute. So it will be a plus b equals n, and then you can still use EQR, not a problem. Yes, good? Yep, that will work too. Of course, if I were you, maybe that would kind of require one extra step for me to write. But it's up to you. It's nothing wrong with it. Okay. All right, any question about this proof here? All right, this one is not too bad. And I will insist that we do one more together with you. At least we do 2 proofs for today. The second one here is going to be a little bit more complicated. Okay? Okay, this one here. Well, this one here is going to be somehow more complicated. At least one way to do it will be the one in the slide. I'm going to follow that one. Okay. To save time, I would suggest I will apply the very first step to filter out all the irrelevant to filter out all the irrelevant hypotheses, and we go from there and let you guys stare at that one for a moment. How about that? But of course, you really got to try to practice yourself to say, without any hints, can you prove this one? That's something I will leave to you, right? All right, so now let's save time. It turns out, to prove this one, which has to do with the Gauss strengthening of MLN, right? That will be the exercise you have to do. So once you have formulated the sequence, you should really check to see at least this one is right. That's the formulation part. And let's now prove it. It turns out, in order to prove this goal over here, we will need 4 hypotheses. We need this one here. We need the linking invariance. We need a safety invariance. We also need a concrete guard. Right? These 4 things are necessary, turns out. Let me now apply monotonicity and then have the new sequence, and I'll let you guys stare at that for one moment to think about how you may proceed. All right? Monotonicity here. So I got B, member of natural number, A plus B plus C equals N, A equals 0 or C equals 0, C larger than 0, turnstile, and larger than 0. Okay? Okay, stare at that for one moment. This one's interesting, actually, but question, or you have some thoughts? Why didn't we take it? It turns out it's not necessary. It turns out. Feel free to keep it as well to see if that might complete your own version of proof. Maybe okay, right? It turns out for the version of proof I have, we don't need it. Okay, yeah. Guys, I'll give you some hints. How about that? Just even save more time. Okay, that's okay. It takes some time. Okay, it turns out we need to consider. You can see we got a disjunctive hypothesis. We can somehow apply one of the rule to split the sequence into 2, right? So that's the ORL rule, which is over here. Before I do that, one of the sequences is going to have this particular hypothesis. The other one is going to have this. Let's say if I talk about the part where I'm going to use this one here, C equals 0. Right? I'm not sure if you see that already. If you see one of the hypotheses say C equals 0, another one says C larger than 0. We have some contradiction here. How can C be larger than and equal at the same time? So by arithmetic, this guy here is false. If you got some false hypothesis, you prove automatically. It's like a false implies anything. All right, so we can get rid of one part quite easily. Okay, that's the easy part. So that means one of the strategy could be you're looking for contradiction in the hypothesis. All right, that's one thing. Another one here could be here. If you look at A equals 0, if I do some substitution over here, A doesn't really matter. So I basically got B plus C equals N. Because A doesn't matter, A is equal to 0. And then combined with the fact that B is natural number, somehow I will be able to show this guy here, somehow. We'll see, okay? Just sketching the idea. All right, let's now try to do it. Okay, so I'm going to apply, number one, the ORL rule over here. And just to remind you, that one there tells you if you got some disjunctive hypothesis, you can split that into 1 and 2. Right? We did some exercises before, right? So after this, we have basically copy the other hypothesis, B natural number, also A plus B plus C equals N. And let's say this one here, A equals 0. And then C larger than 0. Turnstile, N larger than 0. So this is one branch. All right? And let me make it a little bit smaller. This is one of them. And this is another one. Okay, let's write it down. Another one would be, we got B natural number, A plus B plus C equals N, and also C equals 0, C larger than 0, turnstile, N larger than 0, right? Looks like the bottom one might be easier to discharge. Why don't we do the bottom one first? Okay. Okay, we got two sequences. And don't forget, after you apply ORL, it tells you that in order to prove the original one, you have to make sure you prove both this and this. If you stuck it at one of the branches, you didn't prove. Okay? All right, so now for this one here. Well, this one here is like the pink over here, right? You got these two, that should be enough for us to continue. So we don't need these two, all right? So we can apply monotonicity again. And then we got C equals 0, C larger than 0, turnstile, and larger than 0. All right? And we can apply some arithmetic. We say C equals 0 and C larger than 0 is equivalent to false. That one you don't need to explain any further. That's good enough. Okay? All right, so what we got is we got false over here, turnstile, and larger than 0. Oh, let me draw a little bit better. And you can see that this one here, sorry, one more time. There we go. All right, so this one here is definitely matching this one here, right? You can see N larger than 0 is the P. And the false here is the false here, right? Apply this one here. Okay, let's now conclude. For that one, there will be false L. All right, so the bottom branch, done. Now let's take a look at the top branch. What do we need? Let's now try to do a little bit of intermediate steps over here to get us prepared. Okay? First of all, I claim that we only need, why don't we try to do some substitution? Here, I got A equals 0. Why don't we make use of that first? Okay? EQLR. And then we're going to drop that A equals 0 at the same time, which is OK. All right? So where do we have A? We only got A here. That's the only occurrence. So that's the only place. Okay? So we're going to do B is a natural number. 0 plus B plus C equals N. And then we drop A equals 0, C larger than 0, turnstile, and larger than 0. There we go. Okay, that's what we got. Okay. And then if you actually, well, we can also apply a little bit of arithmetic here right away. So 0 here would be canceled out, right? That means we got b is a natural number, and also b plus c equals n, c larger than 0, n larger than 0. Okay, we're almost done. And then, let me know, just make it smaller. There we go. That'll give me enough space. All right? Okay, so if you look at, for example, here, this one here, and this one over here. If b is a natural number, and then you say that b plus c equals n, because somehow we want to get to inequality over here, right? So I would suggest maybe some rewriting here. That one there, I can rewrite it to arithmetic over here, right? Because I know that b is going to be larger than or equal to 0. For something to add to something that's larger than or equal to 0, so I know that b should be less than or equal to n. Less than or equal to, right? You can definitely plug in some number there to try, right? That was also easy. Okay, I just want to make sure nobody got a question, right? Right, let's finish the final part. So c less than or equal to n over here, and also c larger than 0. Turnstile n larger than 0. All right. Now, how do we continue? Well, we're getting there basically, right? So if you look at this one here, right? If I tell you that, if you look at the number line, c itself is guaranteed to be larger than 0. And then I say that n is larger than or equal to c. What does that mean? That means n is also larger than or equal to 0. Or even better, it's actually larger than 0. Say that again. C less than or equal to n tells you that c and n could be the same, or c is actually to the left. But we know that c is to the right of the 0. So it's guaranteed n should be strictly to the left of 0. If you draw the number line, you'll see exactly how that occurs. All right? So finally, I'm going to put a star over here. Okay? So finally, we're going to say by arithmetic, okay, I'll put it here. By arithmetic, we got n larger than 0, and also n larger than 0. Again, we are back to this particular nice terminating rule hypothesis, right? Because you see, the hypothesis and the goal actually match. Okay? You can see we got quite a bit of arithmetic here, which is nice. Just requires some basic manipulation. So let's maybe not in the written test two so much because you'll be mainly multiple choice. But in the actual exam, whenever you actually put the arithmetic ARI, you better make sure you have some side notes to justify why by arithmetic, right? This one here is slightly more complicated, but it's not too bad, right? And don't lose the big picture. The reason that we got this guy here is because we did the hard work from over here to say based on the model that we had, M0 and M1, and based on the proof obligation rule for Gauss strengthening, that's how we generate this particular sequence here. And from there, we try to prove it, right? Luckily, it's provable. So that means as far as the Gauss strengthening is concerned, MLN is good, MLL is also good. Right? That's our conclusion for now. Any questions? Okay, I hope the big picture is clear. But of course, you really got to practice doing this proof. All right, at least we completed 2 proofs today. Yes? You mean here? Okay, good question. It's actually about when I combine these 2 together, I can conclude this one here. Hmm? It's not really removing, it's about rewriting. I'm basically saying combining these two, I'm rewriting it as this guy here. That's what I'm saying. That would be okay. Yeah, it's a little bit different. Either you can completely remove them, but this guy here, this doesn't really appear in the original hypothesis. How do you add it back, right? So I'm basically saying I'm rewriting these two as this one here. So it's a different one. Okay, good question. Now, I'm going to highlight here. So, guys, your classmate's question was good. We are now really trying to remove this one here or this one here, because once we have removed them, we have no basis to really put this one. That's new. So what we're doing is, based on these two, we can conclude that by basic arithmetic that this one should be the hypothesis instead. Okay? Yeah. All right. If no further question, let's now move on. And I think that there will be a few more proof obligations we're going to run into today, but their proof will be very similar, so I can refer you to them to practice yourself. All the solutions are on the slides. You can also refer to them. Right? So now we can focus more on the conceptual stuff. Okay? Okay, so let's now move on to the slides, and let me see what's the next one. Okay, invariant preservation, I believe. Okay, let's now see the slides. Okay, so we're done with this one here. That's the solution to formulation, and then another one. So far, we only talk about the guard strengthening for concrete events. And then we got the proof for the first one, which we did together. And we got the second proof, which is also done. Okay, let's talk about invariant preservation. And there should be no surprise. We already talked about invariant preservation when we talk about M0. The same rule is going to be followed. The only thing that's going to be added to the context will be, now if you look at the invariant here, we got both the abstract invariant, which is I, and the concrete invariant, which is J, right? Not surprising. Okay? So I would suggest we just do it. Okay? Maybe not to prove it, but I'll show you how you can formulate it. The same process ought to be followed. All right, let's now go over quickly. So this will be the proof obligation rule for invariant preservation, specifically for concrete events. So here, and we're going to talk about invariant preservation for new events later. Okay, so just be clear. For concrete events, which is ML out, ML in. Okay, we want to make sure ML out in isolation can preserve every one of the invariants. And also for ML in isolation, you can also preserve every one of the concrete invariants. So based on, let me just finish that. Hypothesis, we got axiom, we got abstract invariance, we got we got axiom over here. We got abstract invariance. Here we got concrete invariance. And here we got the guard for the particular invariant we're talking about. That's a concrete guard. So if you're talking about ML out, preserving the invariance, H should be its guard. When you talk about ML in, preserving the invariance, the H here should be larger than 0 instead, depending on which one you're talking about. And the guy over here is very important, right? Let's now write down the interpretation. The way to interpret this is like this. The concrete invariance, and you can see that here it is indexed into I. And what will be the range of I? It will be from 1 to 5 in our case, right? So the I here is from 1 to 5. So there are 5 of them. We're going to do them individually. So concrete invariants satisfy in the post states. And the post states, somehow we're going to figure that out by using the effects of the events. Right? That's something we'll get into. And if you also remind yourself, the E here is the abstract effects for ML out. the F here is a concrete effects for ML out, for example, right? You can also go back to the notation. That's something we said last time. Okay, let's now try to figure out exactly how they should look like, and I'm going to do one of them. Actually, we can do both of them. That's not a problem. Okay, let's do both of them. Oh, by the way, how many do we have? So here we got H here tells us we got to do for every event. We got 2 events over here. So 2 concrete events multiplied by how many invariant conditions? 5. We got 10. Okay. So here it would be, oh, sorry. It would be over here. There we go. So it would be 2 concrete events multiplied by 5 invariant conditions. So it would be 10. And I'm not going to put all the 10 together. Right? I'm going to put 2 of them. The rest, exercise for you. All right? I'm going to put 2 of them, and I'm going to write down the name. The first one here is going to be about ML out. And then I'm going to put invariant 4. Invariant model 1, number 4. And then that's about invariant preservation. So this is one of them. All right. And there is another one which will be about MLN. MLN, invariant 1, and then let's say condition 5. Right? So you can see different variety. Okay. Let's figure out these 2 together. There will be another 8 that you should know how to do. All right? These 2 arguably could be the most complicated one to derive. Let's do them together. Okay, so the first part here will be about the axiom, right? The first part, the axiom. And the axiom, not here, but that one is about D is a member of natural number, and also D larger than 0. All right? They share the same. So D is a natural number, and also D larger than 0. So that is the axiom. Of course, in the exam or in the test, I'll definitely give you the complete model. But for now, just space. Right? I didn't include them. All right, that's the axiom part. And then we got abstract invariance. I. So the abstract invariance would be these 2. So we got n is a natural number, and also n less than or equal to d. N is a natural number, and also n less than or equal to d. Easy. And then we got concrete invariance, which consists of this one here. All right, I'll write it down once, and then I can do copy and paste in my part. But you should know that they share. So A is a natural number, and also B is a natural number, and also C is a natural number. A plus B plus C equals N, and also A equals 0 or C equals 0, right? Just copy. But you got to make sure you copy the right part, right? That's the main exercise. And for me, I can just copy it. So the same thing over here. Of course, in the exam, sorry, you cannot do that. You got to copy that, by hands, right? Question? Yeah, axiom, basically, if you go back to M0, you'll see those 2 axioms. Somehow, because of space, I didn't include them. Yeah, but if you go back to M0, you'll see the axiom there. Yeah. All right, let's now include the guard, H, concrete guard. For this guy here, because I'm talking about ML out, so I should really put these 2 guards. All right. So let me put, so this will be the concrete guard over here. So this one here would be for ML out, A plus B less than D, C equals 0. The other one, will be for ML in, right? That one will be just C larger than 0. So you got to be very careful, right? And then I got turnstile over here. I got turnstile over here. So also good? Okay, I'll also double check my notes, make sure I'm okay. Yep, good. So what we need is something over here as a single predicate, no prime. Another thing over here, okay, I'll put star here. I'll put star star over here. All right, so that'll be the final part to figure out, to formulate. Okay, for the star, okay, I'll put here star. Okay, star here. The intermediate step is, which invariant condition are we talking about? Number 4. So number 4 is basically here. We're going to give a prime version, which would be A plus B plus C equals N. A plus B plus C equals N. And we're going to prime it, just to say they should be satisfied in the post states. But this will not be the final answer just yet. Right? We have done this exercise a few times already. Right? Now, how do we transform this post-state version into the pre-state version? What do we need? That's something you will need for next Wednesday. You will just need a before-after predicate for the corresponding events. Right? So for ML out over here, the before-after predicate for the abstract version will be M prime is equal to M plus 1. For the concrete version of the events, A prime will be equal to A plus 1. B prime equals B. C prime equals C. Right? Many details here. Got to make sure you really follow. All right? Now, if you want, I'll just do one of them. So you can see here, this one tells you M prime equals M plus 1. And this one tells you A prime equals A plus 1. B prime equals B. And C prime equals C. Right? You can do the replacement. Okay. So A prime is equal to A plus 1. B prime is equal to B. C prime is equal to C. M prime is equal to M plus 1. So you don't need to simplify it. That will be the final answer. All right? So this is what you have to put over here, which I can do that. Plus B plus C plus B plus C equals M plus 1. All right. For completeness, let's now finish this one here. All right. So that one there is going to be star star. The invariant condition that we're doing is invariant 5, which is over here. All right, that's invariant number 5. And prime that in the post states. A prime equals 0 or C prime equals 0. All right. And then what will be the corresponding before-after predicate that we got to think about? We got to use. Because now we're talking about MLN. So here and here. All right. A prime, so this one tells you again, M prime equals M minus 1. This one tells you C prime equals C minus 1, and A prime equals A, and B prime equals B. Right? You just got to know exactly what the before-after predicate is. So A prime is replaced by just A equals 0. Or C prime is equal to C minus 1. All right, so that's the final answer. And I'm going to write it down here. A equals 0 or C minus 1 equals 0. You can see the exercise is really consistent with how we did invariant preservation in the M0. Just the same. The only complication that's added is when you think about the before-after predicates over here, you may have to think about both worlds over here, right? That's an extra complication. All right, any question here? It might seem easy when you watch me doing it. It's not that trivial, so you gotta make sure you practice. That's all I can say, all right? Okay, yeah, especially if you run into trouble doing this, for example, let me know, but it should be straightforward. Well, we have done that many times, right? Right, once we have formulated these two sequence, you will see that I'm gonna leave these 2 pages clean for you. This is the first one that we did, and that's the second one we did. You can try to complete the proofs, okay, exercise. And once you have completed them, the solution are on the slides, all right? And I gave you the hints about what are the relevant inference rules that you can use. And this one seems to be more complicated. You can also try, okay? All right, any questions so far? Yeah? Are you going to be given the list of axiom or inference rule? Yes, you'll be given. So I will include some link in the practice, the actual test, so you can click on the link and see all the rules. But I wouldn't tell you which one are relevant. You got to decide which ones are relevant. So you will not be given something like this, right? You will not be given something like this is a sequence to prove, and these are the ones to apply. No. You will be given a sequence like this, and then you can click on the link to see all the rules that have been taught. You got to decide which ones are going to be used in the test. You might be given anything. You might be given a sequence to begin with, or you might be, you can look at the practice question as well. You might be looking at maybe some, like a proof, like a sequence of steps, and then I want you to fill in the blanks. That's also possible. Yeah. Now take a look at the practice question. That one should give you some idea about what can happen in the test. All right, so this one here, exercise. This one here, exercise. All right. I would suggest we take a very short break by taking attendance, and then we'll continue. All right. And then we'll talk about this diagram after the break. All right, so next one, I would like to talk about this diagram here, which is very fundamental. That one is something called simulation diagram. And there will be some term you have to get yourself familiar with. But let me talk about how to interpret that diagram. Okay. That one basically is about how you can relate abstract transition with concrete transition, right? You kind of put all the necessary background information there. Right, so what you have to learn is the terminology. Whenever you talk about concrete state transition, for example, let's say ML out. It could be the abstract version for ML out. Sorry, concrete version, beg your pardon. Whenever you talk about a concrete version of ML out, whenever it happens, there should be another corresponding abstract version, in this case, ML out as well. Okay? Or, more precisely, if I may just go back very briefly here, if you look at this model comparison here, I'm saying that whenever you try to make a transition by ML out, the concrete version, there should be a corresponding one ML out in the abstract version. They kind of happen concurrently, right? That's what you want to think about, which we did, actually, last time as an informal example. And how do you understand this diagram here? You want to understand, number one, we want to say the concrete event over here is said to be simulated by the abstract events, right? That's the first thing. Okay, so the concrete events over here, we say that there are 2 ways to say that. Okay, concrete. Okay, let me just be more. So concrete over here, and the abstract events over here could be ML out, for example. Okay, so I'd say, for example, ML out. Okay, we say that. Oops, sorry. We say that there are 2 ways to say that. Either you can say the concrete one is simulated by the abstract one. Simulated by, or if you want to go the other direction, you can say the abstract version simulates the concrete one. Okay, if you go this direction here, you can say equivalently simulates.
And this will apply to every pair of abstract and concrete events. All right, so that's terminology. And the interpretation of the diagram is pretty straightforward, but let's go over them carefully. All right. You can think about this part over here, the V and the W, they represent the pre-states of the transition, right? The starting states. So think about the V over here is the abstract pre-states versus the W here is a concrete pre-states. All right, that's where this transition goes. That's where the transition will start. However, it is really important to know that in order for the abstract transition to really occur, the guard for the events, for example, ML, must be enabled. That's why we got G here, to say it must be enabled. Similarly, the concrete guard must be enabled as well. Okay? So this one here is to say the abstract event is enabled. Abstract events enabled. Otherwise, the transition may not occur, right? And this one over here is to say the concrete events enabled. So enabled is very important. All right? Enabled, enabled. And another thing to say, somehow the way we link the V and the W, the two states, is by the concrete invariant, especially the linking variance. Right? So you can think about this one here tells you that the pre-states, the two pre-states, link by the concrete invariance. Right, that's important, especially if you take a look, this one here specifically, right? A plus B plus C equals N. That's the one I'm talking about, right? All right, so the two states are linked together, and also both events are enabled. So now let's make the transition happen, right? So this one is going to transition to the post state here, and this one is going to transition to the post state here. Now we are talking about these two states, right? So these are the two post states. So you can think about here, this will be the abstract post states. And this part over here will be the concrete post states. And also don't forget, the E here is the effects of the abstract events. And the F here is the effect for the concrete events, right? That's also something we spoke about last time. And you got to make sure in the post states, the concrete variance still holds, meaning that the two states are still linked consistently, right? So this one tells you that the two post states still link consistently. All right, almost done for the diagram. And there's a small detail here. You can see that we also say that in the post state for the abstract world, the abstract invariant should also satisfy, right? That's for sure, right? Just for the abstract world. And that one there, you can just don't forget, is also an important detail. The abstract events invariance also preserved. You might be asking, what about concrete invariant being preserved? You can think about this guy here includes that already. Okay? All right, so that's a diagram you will see on the slide. Just make sure you know how to interpret and nicely summarize what's really all the stuff that we have been talking about so far. And you just got to remember, whenever I say concrete events simulated by abstract, or abstract simulates concrete. Okay. All right, any question? All right, we got about 15 minutes. I will suggest the following. Okay. Well, I want to talk about another two events. Before that, the next part over here will be about, let me see, okay. So this will be for ML out, ML in. Oh, okay, nothing new. So basically, remember before the break, we formulated this and this. So it would be your exercise to really try to prove this one here and also prove this one here, right? Okay, I already got hints for you written down, right? You can try. I'll keep them clean. And then the next part over here will be about very easy. That one is about invariant establishment, just the same procedure as what we did for M0. And for that one, we don't need to redo. And this one here will be exercise for you, okay? And once you generate the invariant establishment proof obligation, you can put it here, right? You can also check your answer on the slides. So how many do we need? Basically, it depends on how many invariant conditions you want to establish. In this case, 1, 2, 3, 4, 5. 5 of them, okay? You're going to generate them using the rule. And so here, this will be the effects for abstract. This will be the effect for concrete, right? Once you have formulated the sequence, you can now try to prove these two, which are also very straightforward, right? I can also let you practice. You can use either this or both. That's about invariant establishment. Okay? Questions? Yeah, this is rather straightforward. That's why I'm going to leave that to you guys. But we really talk about the more difficult ones before the break. What I want to spend more time on will be about the new events over here, IL in, IL out. So before that, let me just tell you why we're doing this, right? Just don't lose the big picture. So we're talking about events. So we got N0 abstract model, and also we got M1. And we know that M1 refines M0. That's what we know. All right? And we know that in M1, we actually got two abstract events, ML out, ML in. And correspondingly, we also got ML out, and also we got ML in. So far, we talk about only these two pairs. We talk about invariant establishment. We talk about invariant preservation. We talk about guard strengthening. Okay, and what we're going to talk about next will be another two events, which we call the new events, which only exist in M1. IL in and also IL out. So these are the two that we need to speak about. All right, these two. All right, let's now talk a little bit more about the slides. So these are the abstract events. So these are the concrete events. Okay, good. Let's see the slides. Let's see how far we can go. 10 minutes. All right, that's what we spoke about before the break. And then that's the diagram. All right, and these are the two exercises for you and the solution proof. Okay. Okay, that's the invariant establishment, which I'll leave to you. Okay. Okay, and then that's about the proof for the invariant establishment, which you can also check once you have done the exercises. All right, let's now talk about the new events, IL in, IL out. Okay, if you can remind yourself about the diagram, I believe I have it over here. Okay, let's take a look. If you remind yourself about the two new events, which are here. If you look at the diagram here, ML out is about any cars that actually exit from the mainland and go onto the bridge. And ML in is any car from the bridge back to the mainland. So we need to complete the picture. ILN is some car that actually go from this one-way traffic back to the island. Versus ILL will be any car that is currently in the island, they want to go back to the mainland, going here. Of course, you gotta make sure, for example, when you actually go this way, there better be not any traffic this way, right? Things like that. You gotta put a guard appropriately. So what I want to do is to finish off these two events for the guards and the action, right? And then that might be it for today. All right, so we got the corresponding axiom, variables, invariant, and etc. They are just the same as before. Okay, so we do the similar exercise. I'm going to give you the English description. You tell me what should be the corresponding guard and action. ILN is basically a car entering into the island, right? Going into the island from the bridge. Right, let's talk about guard. When should it be enabled? It should be enabled when the traffic, there should be no collision, basically, right? The traffic should be flowing to the island, but not going to the mainland. All right, that's the first one. And the second one, okay, let's talk about the first one first. ILN is really meant to go this way here. If I really want this to be the case, what should I specify over here? Any suggestion? C is equal to 0? Sure. A is greater than 0 for sure, but C is equal to 0 is also valid. But it turns out one of them may not be necessary. Okay? Let me write down both. I think both are good. I'll first of all write down over here for this one here. Okay? So guard number 1. A should be larger than 0. This is because if there should be a car going from the bridge onto the island, there's got to be at least one car, right? If the bridge is simply empty, how can it be a car, right, going to the island? So 1 should be necessary. But somehow, number 2 over here, when we say C is equal to 0, actually, it turns out this is also necessary because we want to make sure when we go this way here, the traffic should be also not going this way, right? So C should be 0, no problem. Okay, that's good. And what about the action? If I go this way over here to go from here to here, how should I update the variables? Yeah. So B should be incremented and A should be decremented, right? Okay, straightforward. So here we should say A minus 1, and also B plus 1. All right, that's awesome. All right, that's good. All right, and we can do another one. What about IL? That's IL in. What about IL out? IL out will be this event over here. All right, let's now look at the slides. And you know what? For this particular question here, it will require some very small derivation. I will save that part. That will be the final part that's going to be covering the written test too. But that will only take about 5 minutes. I'll use that on Tuesday as first, okay? But let's now finish off the IL out, and then we're done. So IL out will be from, basically, conceptually, from the island onto the bridge, going back to the mainland. Informally, it should be enabled if there is at least some car in the island, right? Otherwise, how can the car go back to the mainland, right? And also, you got to make sure the traffic flow is also correct. All right? So these are the two constraints. All right, this one should be quite easy to specify, okay? Over here. Number 1. You want to make sure, okay, 1 and 2. So there should be at least some cars over here so that you can have IL out. Otherwise, there's no car. to actually go to the bridge. So B here should be larger than 0. Agree? Okay. And then you want to make sure if you want to go this way over here, then the opposite traffic better be 0. So there's no collision. I always remember. All right. What about the action here? That should be very similar to what we did earlier for the ILN. That one there, you're basically decrementing B and incrementing C, right? You're going that way. So B should be decremented and C should be incremented. All right, so these two events are rather straightforward, right? You just need to know the guards and the action. Okay. Okay, so when you review, you're just going to want to pay attention to them. Before after predicates, nothing really surprising. So for this one here, for example, you can see we only cover A and B. So A prime equals A minus 1, B prime equals B plus 1, and C is not mentioned, meaning that implicitly C prime is equal to C, right? You can do something similar for IL out. Right? That's a before after predicate. Okay. I think that would be enough for your written test number 2. So I think for you to study, let me see. Okay, how about this? It will be slide number 69 for your written test number 2. Study up to here. And don't forget, if you refer to the guide, we don't really cover the math review lecture. That will be safe for the exam. So you're going to study the bridge controller. And make sure you also study lab number 2 and 3, the celebrity problem. There might be questions about them. Okay? Okay, any questions? All right, if no, good luck with your study. And I'll reach out to you about a review session, either Sunday or Monday. I'll confirm. All right?